Welcome back to lecture 9.2, where we're going to continue our Everest, but now with non-uniform air density. Okay, what do we mean by non-uniform air density? Well, last time we wrote that the air density, right, we could think of as little m times P over RT, right? Or this was our molar mass. Okay, so now what we mean is now that the density depends on the altitude, okay? So which of our variables are going to depend on the altitude? Well, it certainly isn't going to be our molar mass. We kind of calculated that roughly from the mass of nitrogen. Actually, I forgot to mention last time that we got 29 for air. We roughly calculated 28 for nitrogen. The reason why it's a little heavier is because oxygen is a little heavier than nitrogen. So we could have the pressure vary with height and the temperature vary with height. So let's start with a isothermal process, right, where the temperature doesn't vary. Now, this is probably not a good estimation or not good approximation, right? But it's certainly better than thinking that the density was uniform, right? So this is like our next step of our refinement. Okay, so now we can, write our pressure equation. We said pressure is H plus dH. So now last time we had the pressure was of H. So now we can just think of this as the pressure at a certain altitude plus a small variation, right? Which is just rho g dH. All right, so if we have one altitude, H, then if we want to calculate it H plus dH, well, we're simply just going to have a small correction, rho g dH. Okay, so this is kind of nice now because we can think of this as a differential, dP, which is P of H plus dH minus P of H is minus rho g dH. Okay, so now we're going to simply say that this P, so we're going to sub in our rho, right? So this is going to be dP is going to be minus mPg over RT dH. Or what we really want to do is put our pressure on the other side. dP over P is minus mg over RT dH. Great. So now what we can see is we've got all the pressure dependence over here, our altitude dependence H over here, and mg over RT is going to be a constant. So now we can actually integrate both sides of this. So let's do that. So let's integrate both sides of dP over P and minus, well, let's take our mg over RT dH. Okay, so this is going to be log P. So let's evaluate it. Yeah, so let's be clear on where we're on our limits of value of integration. So let's integrate from P0 to P, right? Starting at some altitude and moving up, starting at sea level and moving up to that same atmosphere. Right, so this is going to be the pressure at sea level and the pressure at the altitude that we pick. Okay, so this is going to be log P minus log P0, right? And minus mg over RT. And this is going to be H minus 0. Great. So this can be rewritten as log P over P0 of minus mg over H over RT. Or take the exponential of both sides, multiply P over. So now P of H, we're going to call it, is P0 e to the minus mgh over RT. So what this means is that we have an exponential decrease in the pressure with altitude, right? Similarly, since we can look at this equation, right? Or this one, regardless. So now we can rewrite rho of H. That was weird. Rho of H. Now how does it depend? Well, exactly in the same way, right? So this is the rho 0, right? The density at sea level, e to the minus mgh over RT. Right? Because when we sub in rho for P, this is going to cancel both the P, the rho and the rho 0. So all those constants would go away. Okay. So what would our pressure be on the top of Everest? On top of Everest, we would get a pressure at 8,840 meters of 1.013 times 10 to the 5 e to the minus 0.029 times 9.81 times 8,840 divided by 8.314 times 300. Take a second, pause the video, and see if you can calculate what that would be. Okay, if you did that, hopefully you got 36,500 pascals, or 36.5 kilopascals. Okay, so that seems quite reasonable, right? Now, cute little thing as a check, right? So here's the check I want you to do. Go look up the pressure. Often it's called the barometric pressure. In Edmonton today. Okay. Now, I always assume that you're in Edmonton when I have this discussion. Obviously, you may not be. So you could also look up the barometric pressure where you are. But Edmonton's a good example because I know what it should be. Okay? So let me actually take a second. Let's look it up. So let's write barometric pressure Edmonton. Okay, so right now, I'm actually getting the right answer. So Edmonton Weather Stats has the right answer. But a lot of places, so even if you were to click on the EAS weather station, so this is the second hit for me, it tells you that today's barometric pressure is 101.6 kilopascals. 101.6 kilopascals is essentially the same as sea level, right? Which isn't right. So actually, if you click on the NATE one, so the fourth or fifth one down for me, it actually tells you that today it has a corrected and an uncorrected barometric pressure. So it calls it the corrected pressure is 101.4 kilopascals, but the uncorrected is 93.7 kilopascals. What on earth does this mean? So this is the correct, this uncorrected is actually the barometric pressure in Edmonton. It's usually around 93 kilopascals because of our altitude. What they've done here, and when you get this weather reporting, they actually correct it so that they assume that you're at sea level and you'd have 101.3 kilopascals. And they're just telling you if you were at sea level, you would be today's would be slightly higher, 0.1 higher than average, right? So they're saying that's a little bit high pressure or almost average pressure. Which is crazy, though, that basically your weather person is basically just simply lying to you constantly. Okay, so we can look at that again in class if people are interested. So if you knew the pressure in Edmonton, now you could work out the altitude. So what is H? So if this is Edmonton, what is H, right? So you could say this was 93 kilopascals. I think it was 101.3 kilopascals. I see I've just put same units on each side. E to the minus all that same stuff, right? And work out what H is. Well, it's not exactly the same stuff. Let's write it out. Minus 0.029 times 9.81 times H over 8.314 times 300. Let me see if you can see that all the way at the far end of the screen. If not, I'll adjust it. Yeah, that looks okay. You can still see that. Okay. Let's take a minute, calculate what that is. Divide this one by this one. You'll have to take the natural log, right? So you'll have natural log of 93 over 101.3 is equal to minus 0.029 times 9.81 times H 8.314 times 300. All right, so you'll just take this. That'll be negative, right, because it's less than 1. Your minus signs will get away. You'll move all that stuff to the other side, and you'll get H. And if you calculate what H is, I calculated 652 meters above sea level. That this is the altitude of Edmonton, and in reality, this is very close. So H Edmonton is about 670 meters above sea level. Very, very close answer. Okay, so this assumption of uniform temperature has gotten us quite close to the right answer, right? So we're within, let's see, not just even 10%, we're within, let's see, are we within 5, maybe like, yeah, something like 3%, right? So we've gotten quite close to the correct answer making this assumption. So we're going to do lecture 9.3. We're going to do one more spot. We're going to actually, one more section. We're going to check this assumption of isothermal, right? We're going to discuss a little bit more accurately what the temperature profile of the atmosphere actually is.